I will turn this over to Ed. As I said in the beginning, I've known Ed for several years. Um, One of the projects, my pet projects, is to develop a manufacturing ship to be able to manufacture at the point of the fight. And it was the Barracuda that we want to use in the pilot project when we have the funding for that. So I will turn it over to Ed Larson and Tampa Deep Sea Explorer.
All right, thank you, Eugene. Can everybody hear me okay? I guess so.
Yeah, I can hear you.
Okay. So
I can hear you.
Oh, good.
Okay, good. I'm going to share my screen real quick, and my presentation's not so long, so you won't, we'll just keep it moving here. I think this is the one I want to share.
And I didn't have time to spend with Bill to explain to him meat and potatoes on paper plates.
Oh, yeah. Let's see, there we go. Okay, so I'm Ed Larson with Tampa Deep Sea Explorers, and we are a manufacturer here in Tampa, and we manufacture a small autonomous underwater vehicle that we call the Barracuda AUV. And so the whole purpose of the company, we started off in the Shell Ocean Discovery X Prize, which was a competition to map 100 square kilometers of ocean bottom to a depth of 4,000 meters in a 24-hour period. We were participants in that competition. We were semifinalists, and there was a smaller piece of that competition called the NOAA Bonus Challenge, and we were second place in the NOAA Bonus Challenge portion of that competition. So the Barracuda AUV came out of that development, and since then we have developed it further. The picture shows fourth generation prototype of the vehicle. We are currently in fifth generation and beginning our first round of production, and we have a dozen of these placed. We have another soft orders for another dozen, and then our first production run of 30 vehicles. We still have approximately 6 of those vehicles that we will need to place by the end of the year. And so as our mission statement says, we're passionate about data collection in the deep sea, and we are trying to produce professional quality vehicles that can reach great depths and collect workable data, but at a significantly lower cost to those who are our customers and users. So the problem that we're trying to address, underwater vehicles tend to be large, expensive, and difficult to operate, and they have a long logistics chain. And so our solution is to try to produce a low-cost vehicle that is substantially less than what's available on the market, but that has the capabilities equal to or superior to comparable vehicles. And we want these vehicles to be serviceable and usable to the end user, and easily deployable and recoverable. So what came out of the X Prize competition is the Barracuda. It is a little over 1 meter long, about 35 pounds, but capable of reaching 600 meters depth. That depth has been tested at USF in their pressure tank. We've successfully tested these to 800 PSI. That is not crush depth. That is a working, that was a successful test. We have not yet tested the vehicle to crush depth. We hope to be able to reach at least 1,000 PSI before crush. And we plan on testing that soon at USF. So the vehicle itself, the base model is about 20,000, which puts us actually an order of magnitude below comparable vehicles on the market. It is a sensor platform, so it's able to carry a wide variety of sensors. In the picture there, you see an Allied Scout 2 side scan sonar that we were testing for drag and weight in the pool. And the vehicle itself is modular open source architecture. Everything on the vehicle is modular. Everything is replaceable in the field with using just normal hand tools. There are no specialized tools required. There are very few proprietary parts. The body and the battery are the two main proprietary pieces to this. Everything else is commercial off the shelf. So a sailor or a worker offshore can stock spares easily and relatively cheaply. With the competing vehicles, usually the motor is proprietary. So if you burn out the motor, that's several $1,000s. The motors on our vehicle are not. They're commercially available. The ones shown in the picture are about $75 a pair. The ones that we are currently moving towards, either Apis Queen, which is a Chinese manufactured motor, or Blue Robotics, which is a US sourced comparable motor. They are anywhere from $150 to $250 per pair, considerably less than proprietary parts. Internally, we have an autopilot, which is a commercial autopilot that's used in aerial drones. Right now, it's Orange Cube. This can be upgraded to other autopilots, and we can also integrate other inertial navigation systems that are commercially available. The only real limitation there is size and weight. Internally, we have a payload area about 10 inches long, up to about 2 pounds we can carry internally. And if needed, we can add a 10-inch extension on the front. You see that in the technology picture. That extension adds about 5 pounds of additional payload capability. In that picture, we're showing a mock-up of a LiDAR system that we are currently developing. Somebody have a question? No? Okay. So anyway, our journey, we started in about 2016 in the X Prize. That competition ended in 2019. And we won some money there and formed the company. And since then, we've been developing the technology, primarily the Barracuda AUV, but we are involved in 2 grants right now. One, and I'll talk about this more in a moment, but one is phase 2 NOAA grant to develop compact subsea LiDAR for our vehicle. There are subsea LiDARs available, but nothing on the market that will fit on a micro or mini AUV or ROV. Our vehicle is based on a 4-inch diameter Blue Robotics end cap. So once the LiDAR is available, it'll be easily adaptable to any vehicle using a 4-inch Blue Robotics body. And the main limitation there is the housing, which can be modified as well to accommodate larger body sizes. So I mentioned the LiDAR, and the LiDAR development is currently NOAA phase 2. If you can see it in the camera, this is a mock-up of the LiDAR. It's changed a little bit since this mock-up was made, but it'll be a little bit longer than this and weigh approximately 7 pounds in air and less than 5 pounds in the water.
Ed, can you stop sharing so that people can see that for a second?
Oh, okay, sure. Okay, let's see. Now I've got to switch So I can see. Okay, so yeah, so if you can see it, this is the LiDAR mock-up.
So that would all your payloads be plug and play like this?
Yes, that is one of our goals, is to make everything easily integrated to the vehicle. Internally, we use a Nvidia Nano as our CPU, and so that has a Ethernet interface. It has a USB interfaces, UART, and SBI and I2C interfaces. So we can interface to a wide variety of sensors, and we are partnered with another company called BeamC that's making the LiDAR. This will be integrated to the vehicle using an Ethernet connection. And so Blue Robotics, they use Raspberry Pi, which has an Ethernet interface. The Orin has an Ethernet interface. Both of them are using Debian Linux. And so the software that we're writing to integrate to our vehicle should be easily adaptable to Blue Robotics vehicle as well.
All right, thank you.
Yeah, you're welcome. Let's see. I'm going to switch to a different slide presentation, slightly different. So our roadmap up to this point, we have had a couple different grants. One of the other grants that we are in is with SOCOM, and we're collaborating with BeamC and Certus Core, who is the primary on that grant for SOCOM, and that is to develop a subsea communications network. And what we're doing there is a hybrid system, which is a hybrid between optical and acoustic communications. And it's based upon the development of the LiDAR. What's going to happen with that is that the LiDAR head, it'll be modified to serve as an optical communications node. And so using acoustic modems, the vehicles can localize and align themselves with each other while they're performing missions in the water. One possible use case, maybe it's a search and find mission where we're using LiDAR or imaging sonar to locate an object. Once the object is located, the vehicle will take pictures and record its location, and then it will do a broadcast message to the rest of the swarm that it has achieved the goal. The nearest vehicle to the one that finds it, they will align themselves using the acoustic system, and then once they are properly aligned at depth and distance, they'll do an optical handshake through the optical node. After that, all the communications is transferred optically. So that's high speed. In this phase, it's a phase 2 STTR. In this phase, we're hoping to achieve between 5 and 10 megabits per second in a communications window, approximately 20 to 30 seconds in duration. This should be enough time to transfer, say, a still picture, localized information, coordinates, depth, etc. And once the communication is transfer has occurred, that second vehicle will then transfer that data to a communications buoy that acts as the aggregation node. Now, it's assumed that the communications buoy is located in some safe space where it's able to be anchored and communicate. And the vehicles themselves were simulating that we'd be maybe in a hazardous space. So whatever number of relays need to occur for the communications to be transferred, then it's transferred to the buoy. And then once up the buoy has surface radio and Wi-Fi connections that the information can be then transferred to surface operators. That's the intention in this phase 2. In the follow-on phase, it's planned
Ed,
that all the communication buoy information will be integrated to a vehicle and that we won't need the communications buoy. Yeah, go ahead.
Ed, do you want us to be seeing your slides right now? Because we're not.
Oh, I'm sorry.
That's all right.
I thought I clicked on share again. Guess not.
That's okay. You're doing a good job of explaining it, so I was able to visualize it. That's why I wasn't
Yeah,
quite sure if you
pictures
wanted us
gives
to
so
see the
much
slides
better,
or not.
right? There you go. Yeah, pictures are worth 1,000 words, though. But okay, so yeah, the idea here is that a number of these Barracuda AUVs will be involved in a search pattern, working independently of each other and not necessarily needing to communicate with each other. They're just searching their particular area. Then once the object is located, the communications transfer occurs, relayed back to the surface buoy, and then communicate to the shore. In later developments, the communication buoy will be eliminated, and it'll be ship to ship with the Barracuda AUV, and then the Barracuda, the last one, will either move to a safe space and surface and communicate the information via surface, or some type of optical transfer, possibly to an aerial drone or to a ship without breaking the surface. That was expressed as a major interest at Soft Week a few weeks ago. We were there with Certus Core and spoke with several of the potential users of this, and that's what they consider to be a real killer app for this. If we could do submarine to aerial or submarine to ship without breaking the surface, which I have a couple ideas around how we might approach that.
Hey Ed, can you get rid of your notes section so we can actually see most of your slide?
My notes section.
If you can go into presentation mode.
Version.
Well, I am in presentation mode.
Yeah, it's not coming up that way.
I'm not sure what you're seeing.
So in presentation mode, you're seeing what the presenter would see, and then if a second monitor would see just the slides. So you've got your notes up that if you'd had a notes section for the presenter to read, the audience doesn't see those.
Well, I'm not sure why that's even visible. I'm going to close a couple of these just because somewhere something is not.
I'm gonna go ahead and run it from my computer, Ed, and then
Okay,
that way I think that'd be easier way to go.
Okay. What about that? Do you still see the notes section?
We're not seeing anything right now, so I'll go ahead and run it.
Okay. Okay, so
All
we're
right,
on slide 7.
is everybody seeing that? Are you
Yeah, I
seeing your
see it.
presentation? Okay, so just tell me when to change.
Yeah, go ahead. Slide 7 is the one that we're on.
Tell me when. I don't have numbers on here.
Oh, okay, keep going.
NOAA phase 2. There we go.
Yeah, my screen didn't change. I don't know.
I got the compact low cost AUV platform.
Yeah, I see the problem, cost, technology, complexity. I don't see that slide.
Let me try this again.
Yeah, there you go. Okay, so in addition to the LiDAR and the subsea communications, we've done some other work with some other collaborators. One of them is, if you look at the Barracuda picture, you'll see the motors are on the dive planes rather than at the rear. Most traditional AUVs use a prop and a rudder for steering, and this means that to turn around, it takes them, a radius of about 10 feet or more. We put the motors on the center of gravity, and we steer by differential thrust. We can turn a full 360 within the body length of the vehicle. We can turn very sharp. We can also back up, and we can back out of tight places. If we get into a corner, a box, or even if we go in through a hatch or something, we can actually back out, where a lot of similar vehicles can't do that. So this is actually a superior feature of our vehicle over others. It's actually the subject of a utility patent that we hold. And this makes the vehicle very user-friendly. It also makes it easy to modify. The body structure is a 4-inch tube that runs the length of this vehicle, and then the streamlining is done with the molded syntactic foam body. So if I want to add something externally to this body, I can simply drill into the syntactic foam and put screw mounts and then screw into it. And I don't compromise the integrity of the cylinder of the vehicle or the depth capability or anything. And it also has a minimal impact on the streamlining of the vehicle. A lot of other AUVs are aluminum, steel, or composites, and you're not able to do that. You can't drill into it without compromising it. All of our connections are run under channels underneath the fins. Each of those fins has a conduit that runs from the wing root of the vehicle all the way back to the back of the fin. So if I want to add a light, you see this picture with a beacon light. I just drill down until I hit the conduit, and then I can mount my screw mounts, mount the light, run the cable to the back, and then it goes through the bulkhead at the back. All connections are done on a single bulkhead at the back. This is how we achieve a really good depth capability without compromising the strength of the vehicle. Okay, go ahead to the next slide. So we've sustained ourselves up to this point with primarily grants. I said a couple of NOAA grants, a couple of STTRs. We also participated in a couple other SBIRs that were not really related to this work. We've received a number of awards last year. We received 2 innovation awards at Tech Connect for the LiDAR development. I'll be at Tech Connect next month to present the Underwater Communications Network and our follow-on. I'll be displaying the Barracuda in its current form at that. We've also received some local awards. We received an innovation award from Tampa Bay Business Journal, again, around this LiDAR and sensor development work. And next slide. Okay, so our roadmap, we've begun initial production of the Barracuda AUV. Later this year, we'll be finishing and testing the compact LiDAR. We should be doing in-water testing in a month or 2 with the LiDAR system. And then next year, we should see the conclusion of the network communications development. And what this does, this will provide us with swarm capability with the Barracuda, so we can complete complex missions with multiple vehicles. And again, the vehicle is cheap enough that even with a swarm, it'd be less expensive than some of the larger AUVs on the market. And there's also missions that you can complete with multiple vehicles that you can't do with a single vehicle.
What sort of ranges are you looking at for your comm?
The optical communications right now, we're expecting between 3 meters to 50 meters, depending on the water clarity. But the vehicle will sense the turbidity, and we'll adjust the communications distance based on that. It's you're probably aware, optical communications through the water is difficult beyond about 50 meters distance. The laser gets attenuated by the water, also starts to diverge, and much beyond that is pretty difficult to do. We have additional.
Ed, are you tied to a specific optical modem or excuse me, optical communication system, or is that interchangeable like the props and stuff?
Well, right now that communications node is based on our LiDAR development, and it's actually a modified version of our LiDAR system. So it would be specific to the LiDAR. That would be something that's not commercial off the shelf.
Okay, yeah, because I know I've worked with underwater optics that talk about ranges of 100 meters.
Yeah. Well, to achieve that, it'd probably be crystal clear water. I have seen that. There's a Swedish company, I believe, that's doing an optical communications node. They're doing like a vertical communications from subsea platforms, and they claim a range up to about 100 meters. But we'll know better once we do some in-water testing. Right now, the system's still being built. But like I said, our projection is 3 to 50.
Yeah. So would you be able to share, especially for the federal market, where and when you'll be doing testing, so that people could attend if it was
Yeah,
possible?
actually, I can share that. That as part of this STTR, the plan is to do the initial testing at Channelside over by the Liberty ship at
Okay.
Channelside. And that'll be a demo for SOCOM when we get to that point. But this development right now is unclassified. And so I would expect that other agencies, other military agencies and federal agencies should probably be able to attend that. Probably need an invite, but probably no more than that.
All right. Yeah, I'd like to share that when that's set up.
Okay.
I can because
Yeah.
I can share it with just the federal community if
Yeah. Yeah. And we're not primary on that. Certus Core is, and we'll bounce that off them, but I don't see that there'd be any real problem with that.
All right. Thank you.
Yeah. Let's see, next slide, I think we can move to. We have some other developments for the Barracuda. We plan to scale it up by 50% to increase battery duration. Right now, the mission duration is 4 to 5 hours on the current battery. If we scale up the vehicle by 50%, we should be able to get in the range of 12 to 18-hour duration, which would be pretty competitive with similar sized vehicles. This is some of the potential customers. We've talked to a number of offshore energy companies. I was at Sea Japan last month. There's quite a bit of interest in the Barracuda in the Japanese market, and particularly in offshore energy. Japan's doing a lot of development with all types of offshore energy for obvious reasons, I guess. They're constrained when it comes to land-based stuff. Research, our initial target for the vehicle was small research institutions and small businesses where they could afford to buy one of these with a SBIR grant versus renting a more expensive AUV, where at the end of the project, they would just have the data, whereas with us, they would have an asset that they could reuse over and over again at the end of their grant. What we found, however, is that we have considerable interest in this from DoD and other government agencies. NOAA's interest in the LiDAR has to do with data collection for things like shipping channels, et cetera, after hurricanes and large storms. The vehicle is small enough and cheap enough that it can be pre-placed at the site of the storm and can be deployed from shore or a small vessel. I've successfully launched and recovered this vehicle from a canoe without falling in the water. So you can launch it from virtually any vessel. Next slide.
That's all I got.
Okay, so I don't have the pitch. Okay, go ahead. We don't need the slides then. So we're currently raising funds. We're looking at seed round between $100,000 and $500,000, and shortly after that, our current burn rate is a little over $20,000 a month. So 250,000, for instance, would be enough to sustain us for a year. After that, we're looking at a seed round of around 5 million. Our plans for that is to scale up production, acquire our own production facility. We have a shop here in Tampa, but we rent it, and it's a small space, and we can produce 5 to 10 of these a month in this space. If we begin to produce more than that, we will need larger space, and that's what the seed round would be for, plus additional products. Obviously, we have some plans for further development of this vehicle. We also have plans for additional vehicles and additional sensor options as we move forward. And we expect once the vehicle is adopted on the market, there'll be a lot of integration work, integrating various sensors and payloads to this as well. So that is us. I think that's my presentation. Are there any questions?
Okay, you don't have to raise your hand if you want to ask a question. I do have a couple, Ed, that I made note of.
Sure.
So one of your points is that it's not cost prohibitive. These are not cost prohibitive. Could they be used with attritable at payloads?
Yeah, we've actually had several questions about this as an attritable item in, say, the Defense Department. The current payload is about 2 pounds internally, which doesn't give you much. But from a reconnaissance point of view, though, if it's a recon device, yeah, with the subsea communications network, these could be attritable and not necessarily needed to be retrieved. It could be scuttled fairly easily at sea. With the 10-inch extension, we can get an additional 5 pounds. And I made the point to somebody, a 5-pound shaped charge, punch a pretty good hole in a ship hull, if that's what you wanted to do.
Yeah, not necessarily just kinetics, but a lot of
but
EW applications and sensing applications where.
Yeah, and that's true. These are cheap enough. They're 20K base and then additional sensors, but they stay under 100K fully outfitted. So yeah, these if mission requirements were such that you had to collect some data or deliver something without really needing to recover the vehicle, that's certainly within the realm of the price is within the realm of something that would be worthwhile. Also, the ability to carry external payload by removing that top fin. We've carried a SLUAS canister 3 inches in diameter and about 12 pounds in weight, and successfully released that as a demonstration. So external payloads can be carried, and let's say you had something that was too large to fit internally, you put it in a 3-inch diameter canister and carry it externally on the vehicle and still deliver it.
All right. So Mr. LaHue, you want to go ahead?
Yeah, I was just wondering, I mean, from military wise, a lot of times we are kind of stuck in our old pipelines of how we think of it. Do you see a mission set that we're not necessarily been inquiring about that you think the tech is right for? And then another simple question, can it be airdropped?
Yeah, well, those are good questions. Airdrop might be difficult because of the dive planes. We did participate in the Navy's air deliverable subsea glider, which we weren't selected for, but we have looked at, say, deploying something similar from, say, a helicopter or from a hydrophone launch tube. So we have looked at that, but that would require additional development for that. Other use cases, yeah, there's a lot of potential use cases for this that haven't necessarily been looked at. One of the reasons I think is, well, a couple of reasons. technology development in the underwater space is quite a bit slower than on the surface. A generation in this type of equipment's about 20 years. And a lot of what's being used out there has been around for several decades. I think one of the limitations has been subsea communications. Once you have the ability to network multiple vehicles together in a covert manner without giving themselves away, I think it opens up a lot of use cases that haven't previously been tried. Some of this fleet security, harbor security, diver identification, mine inspections. One of the use cases potentially for this with kind of paramilitary, the port authority, when a cruise ship comes in, they have to actually go out and search the path for contraband that might have been thrown overboard. This vehicle can move at up to 6 knots, which is considerably faster than a diver can move, with a trainable, AI trainable GPU on board to recognize packages and patterns. You could potentially use this to locate firearms that were thrown overboard, drug packages and things like that. There's a lot of those types of cases that I think need a little bit more thought, but I think could definitely be an outgrowth of this type of vehicle.
All right, sir. Did you have another question?
No, I'm good.
All right. So sustainability. So, there are battery options are becoming more and more diverse. And, there are, the nuclear waste batteries, which basically have a 15-year life cycle or lifespan. How durable would this be for extended duration? Since you are doing studies, you're looking at this as mapping and environmental issues. Would that be, how would that work?
Yeah, right now we use a lithium ion battery. There are some higher energy density batteries out there, and we've had some talks with some other vendors. Graphene-based batteries, high-density capacitor arrays, some of the ceramic batteries that are used in various applications. And yeah, we're definitely looking for alternate chemistries and things that might extend the useful life or the mission life of the vehicle. We're definitely always looking at things like that. One of the things we want to do and follow on, seawater batteries are available for some vehicles. We would like to develop one, not necessarily for this size, but the scaled up 50% scaled Barracuda AUV. We think a seawater battery is a viable option, and that can extend mission duration to 24 or 48 hours. Something like a nuclear decay battery, I don't know how heavy they are. That's the main thing, is space and weight considerations are the limiting factors. In the underwater space, you have to offset weight with buoyancy, and that means displacement, and that determines the size of the vehicle. As things get heavier, then things get bigger.
Right.
And
No, I understand.
yeah.
So and that was another question that I was going to ask. So you are scalable from the 3 meter to larger?
We plan on scaling the vehicle up 50% and also scaling it down 25%. The scaled down version would most likely be a tethered, strictly tethered vehicle for, putting in the water and getting a quick picture, doing a quick inspection, that type of thing. The scaled up version, larger battery capacity, extended range, potentially deeper depth capability, even though 600 meters is pretty good. I mean,
Yeah.
99% of the time you probably won't go deeper than that. The Navy will, but nobody else will. But yeah, the scaled up version will obviously be able to carry larger payloads, larger arrays of sensors, and some of the equipment that simply is too big for the Barracuda, the small version, to handle. But that's how we see the that product line developing. In addition to that, we would like to do an autonomous boat, and we would like to do a subsea glider. As we talked about, we had bid for air launchable subsea glider, which the Navy didn't pick up on our proposal, but we would still like to pursue that because we think, again, that's a very doable project for us, and also could be very large demand for that once it's developed.
You know, AFRL had developed a cage for deploying a jet ski, basically.
Yeah.
That would protect the jet ski, and then as soon as it hit the water, it would break away and sink. So I would think something like that could be viable as well.
Yeah. Yeah. Well, then in that type of scenario, yeah, we could definitely air launch or airdrop a Barracuda.
A cradle. I was trying to think of the word, a cradle. There we go.
I do like the idea, though, of like a scissor wing subsea glider that would fold up and fit in that 5-inch standard launch tube. That
would allow it to be pushed out of a sub as well.
Yeah, sub and helicopter and C-130.
Right.
All of those. Yeah. And yeah, I think that would be a good development.
All right, and I had one last question. And when you were talking about the propulsion, that you were saying that you vary the speed of the propellers.
Yeah.
Does the mechanism turn at all? Could you surface horizontally? And
No.
and then the other thing too is you had talked about that you could use other propulsion units. How would those attach? Is that, I mean, could you use, are there just like 2 options, 3 options, or basically anything that you pull off a shelf?
Yeah. Well, the only real difference for the motor selection is the mount, and that mount is a metal tube about 6 inches long with a bracket that fits the mounting bracket of the motor. So right now we have 2 iterations of that. If you want to switch from, say, the off-the-shelf brushless motor to Blue Robotics T200, you would need to that piece, but it'd be the only piece that you'd have to change to make that change. All the connections, all of the ESCs internally, all that stays the same. As far as the degrees of freedom, the vehicle has approximately 3.5 degrees of freedom, and so we have pitch, we have yaw, we have forward and back. We don't currently in this version have roll control on this vehicle. It's all ballasted at the bottom. When we turn into a turn, it does just like an airplane. It banks slightly, but then resumes horizontal at the end of the bank. In this next version, the scaled up version, we will add roll control by adding a small vertical thruster in the dive planes. So that gives us a couple additional capabilities. That gives us 5 degrees of freedom. and will also give us a hover capability. Currently, the Barracuda AUV in its current form, we weight it to nearly neutral buoyant. You can stop, but you can't hover for a prolonged period of time. It'll begin
Okay.
to rise because of it's slightly positive buoyant. But in the next version, the scaled up version, we will have the ability to hover and to roll and to pitch. To answer your other question, there are no moving surfaces on the outside of the vehicle except for the motors. The dive planes are fixed. The pitch control is done by shifting the battery internally, which changes the center of gravity. So it allows us to pitch down and up about 15 degrees. And then dynamic force on the dive planes will give us an additional about 15 more degrees of pitch when we're in operation. So we can pitch down up to about 30 degrees, pitch up an equal amount. And so this was done when we were in the X Prize competition. We designed the original Barracuda like this because of the depth requirement. And we wanted to make it as simple as possible without any moving surfaces on the outside, because those are potential points of failure with the vehicle. Most of the other, like subsea gliders and some of the other AUVs, they have movable surfaces externally. And depending on the vehicle, some of them are pretty adjustable. Some of them are like on-off type of controls, so they're not not as good. Whereas our pitch control is very fine. We can move that battery by fractions of an inch and really fine tune our pitch with that.
Okay.
Yeah. So I hope that answered your questions.
Yeah, no, it does. A lot of good information there. I appreciate that.
Yeah, you're welcome.
All right, so I'll open it up again to the community. Jeremy, you got something?
This might not be your primary focus, but when you were talking about the sea gliders and then getting things scaled down to be deployable, you mentioned the C-130 Hercules, but the first thing that I thought of was like the P-8 Poseidon and the possibility for everything from civilian shipping lane clearance to active mine searching and maybe demining activities. I think these might be a little expensive for that, but a loitering capacity and a maneuvering capacity, even maybe a report back capacity, so you don't have to either risk the destruction of your device when it detects a mine or many other features along those lines. I was curious if you'd sought out those kind of applications.
Not yet. I think that some of that we'll look at more in depth once we have this subsea communications network working, because yeah, I see a lot of potential there where you might have an information relay where you need to send this information 20 miles but the vehicles have a range of 10 or something like that, where they could rendezvous and transfer the information and actually go almost any distance at that point. So that kind of thing I can see. And like you said, for anti-mine type operations, yeah, these might be sacrificable devices, or they might, we were involved in a thing at Softworks several years ago about infrared detectors, and one of the things we came up with would trigger an infrared detector from about 50 or 60 feet away. It's potential that we could do something like that around mine, depending on the type of mine, cause it to detonate remotely or without having to sacrifice the vehicle. Obviously, you don't want to do that on a shipborne mine, but something that's on the bottom or in open water, you might do that.
I may have missed this earlier in your discussion, but we were talking about communications network. Are you, is this a point and node, so it's the buoy is the only communication, or do you envision deploying multiple of these and having them function kind of as a mesh network?
Yeah, ultimately, we're planning on it to be a type of mesh network. Right now, in this current iteration, it's single mode, point to point, Eventually, we want it to be multi-mode, point to multiple points, and also to be bidirectional. Right now, it's basically half duplex communications. We'd like to get eventually to full duplex communications, where multiple vehicles can communicate with, let's say, the one that has the vital information simultaneously. But that does take a little bit additional development.
Okay, so I'm gonna ping on the SoftWorks people. Dennis, Brian, are you still there?
I am. Brian had to step out. I know he has talked to Ed before, and Ed, he did say he was going to reach out to you on a couple other things. So
Okay.
So what about the using this with the underwater RF that we were talking about last Wednesday?
yeah, I think that's definitely a good idea, and certainly something doable. We just got to get it in front of the right people.
Yeah, because I think that, you know, because it's Denny, I think is the representative for them.
Yeah, and by the way, yeah, I did reach out to him. Haven't heard back yet.
Okay, all right. Yeah, I can reach out to Mark Berry. I think he's the CEO.
Okay.
All right, thanks.
Yeah. Thank
Hey.
you.
Anybody else have anything?
I have a question.
Go ahead, Brian.
Ed, can you give just a brief rundown on how you could see using your ROV for saltwater to freshwater inspections after a storm for, say, the Corps of Engineers to inspect either the base of a dam or eroded pipeline as the pipeline crosses a river channel?
Yeah. There's a couple different approaches you could do there. You're talking about in brackish water, where it's a mix of salt water and fresh water. Sometimes it's a difficult transition. Yeah.
Yeah, with the varying densities and the turbulence of the water.
Yeah. So to do that, you just need to add you would need to add a sensor for velocity of sound through water, and then you can adjust for your sonar and your acoustic communications dynamically. It is something I've looked at. I've looked at a real simple solution for our vehicle for speed of sound through water that would enable that type of operation. And then in that situation where you have a post-storm and it's turbid water, you may not want to use the LiDAR, but we could integrate a forward imaging sonar and probably do pretty good work with that. And then the only real limitation, like I said, would be to dynamically adjust for that water density as it's changing.
Is your vehicle's 6-knot forward speed maximum, is that enough to deal with running water like a river downstream of a dam, or especially post-storm, you've got stronger runoff?
It depends. Yeah, that's the thing. We have to do some tests on that. We think that up to about 3 knots we can compensate by tacking, just like an airplane tacks into the wind. But beyond that, we would probably have some difficulty. But 6 knots is what we've measured up to this point. We are hoping eventually to be able to get the vehicle to about 12 knots. And at that speed, we can probably compensate for up to about 6 knots of current. Beyond that, we might not be able to in the smaller version. The larger version will have larger motors and more thrust capability.
But you for those applications, though, you could always use a guy line across because you know exactly
Yes.
where you're looking. It's not like you're looking over a large area.
And our vehicle can be tethered, yeah. So
Yeah, so
you can tether it and hopefully you can keep it oriented in the stream where you need it to be for sure. But yeah, in that case, you would want a tagline.
okay, yeah. So that's all I have. Anybody else? Okay, so Ed, the one thing that is missing from your presentation, I did not see your contact information everywhere. So
I
if you could
know.
go ahead and put that in the chat, I won't kick
Yeah.
you out until that shows up in the chat so that people can get that. And then and send me an updated slide deck with that on the last page.
Okay.
Yeah, website, email, that kind of stuff.
Yeah, sorry about that. I noticed that too. We need to get that in the deck. Also, Joe, you're on the call. Put your information in the chat as well. Joe's our COO, and would be happy to talk to anybody.
I am happy to talk to anybody. So, especially if you're interested in investing. So, I think, we are on the verge of, doing some really great things here. We've been together for 7 years. And, we've got things going all over the place. And we get additional funding. We may need some help from some of you guys.
There you go.
Yeah.
That's what we're here for. So yeah, I mean, and keep us up to date, because the recording will go up on the YouTube channel, and you're always welcome to go in after the fact and add comments, add updates to your video. Whatever it is that you want to do, it's open for you guys to do that.
All right, I appreciate it. Thank you, Eugene, for inviting us.
Very
Yeah,
much.
no, I think this went really well.
Yeah, and it's good to see you at Softly.
Yeah, no, yeah. Gosh, that what a week. I didn't sit down for 4 days. Tell you.
Yeah, my feet were sore.
Yeah.
Yeah.
But no, a lot of good people, a lot of good connections, a lot of good technologies there. It was quite fascinating.
Yeah, we made some good contacts. I've been doing some follow up this week with some people we talked to there as well. It's always I mean, those kind of events are always really good.
Yeah. Yeah, no, I probably sent out 50 requests for presentations.
Oh yeah.
Yeah, what? I mean, there was almost 1,000 exhibitors there. I mean, that's just
At least.
just
I
a
used to
scratch
run
on the
that
surface.
conference, and there were 1,000 back then. It was, I don't know what they're doing now. It's crazy. You can't see everybody.
No, you can't. I like I said, I went to the JW Marriott and spent all day there.
Yeah.
The first day, just on that floor.
Yeah, yeah. I tried to get over the main. I got over the main building a couple times, but yeah, just to walk around and see, just to see all the booths took quite a bit of time, and then you had to be kind of selective in who you talk to because
Yeah.
you couldn't talk to everybody. But yeah, thank you again, Eugene.